The second example I have here is from a paper looking at the relationship between body mass index and body fat percentage. And this is quite an interesting paper because we do use BMI as a proxy for body fat in all sorts of contexts, just because actual body fat is a lot more time consuming and difficult to measure than a simple BMI calculation. This one is done particularly in Vietnamese people because they're looking at whether or not standard guidelines are appropriate in this context. But we're just going to look at their regression results. And again, the links to the paper is there. So if we have a look at how they've done their data analysis, I've sort of redacted this a little bit, not because I think you shouldn't read it, but just because we aren't actually covering Bayesian statistics and I don't want you to be distracted by it. So they've said that they have used a multiple linear regression model, and they've actually given us the equation. Again, if I get my pointer out. So they've said the equation is percentage body fat is equal to some constant plus an adjustment for their gender plus an adjustment for their age plus something to do with their BMI, and then we've got another BMI term which is squared, and this would be an indication of a curve, and we can see that in the following graph. And then they say the assumptions of linear regression were satisfied, so they've looked at the normal distribution, homogeneity of variances, and independent errors. So that's quite nice that they've put this sentence in here. A lot of papers wouldn't write that, and they've done their particular analysis in R. Okay, so let's have a look at their picture to see what's going on. So is there a relationship between BMI and body fat? Well, there is, and this is a good thing because we use it all the time as a measure, but it's not perfect, and it's perhaps a lot less perfect than you might expect given how ubiquitous it is to use BMI as a measure, a proxy measurement for body fat percentage. Here we can see that a straight line seems to be fitting for most of it, but then it's got a little kink at the end, a bit of a curve, and that's where that that's where the BMI squared term was coming in. That's giving us this little bit of curve here. You can also see here that they have fit a separate line for the males and the females, and that's not unexpected for a measurement like body fat. And they haven't represented age on this graph. That would be quite tricky to put another variable on the graph and to make it still easy to read. And you can see that we've got a shaded band in here for the confidence intervals, and we're a lot less sure of this relationship at this end where we have less data than we are in the middle, similar to the one I used in the lecture. In terms of how they write this model out, they've given us two different models. Again, and this is not unusual for people to try fitting different models to their data to find out what's going to give us the best explanation. We're not covering Bayesian statistics, so just ignore the Bayesian stuff. You can sort of consider the credible intervals to be equivalent to a confidence interval in this context. And here we've got the regression coefficients, which might be represented by B or a beta in another paper. And then they've given us the R squareds down below. And we're getting quite a high R squared, which we would hope for, especially if we're looking at the relationship between a variable and its proxy. So if we're going to estimate body fat percentage with BMI, we would want that to be a good relationship. Whether or not that's high enough, or you think that's good enough, I don't know, I'll leave that to you. So that's about 70%, a bit higher for the second model. And so if you wanted to write out the equation, and which they did in the second slide, then you could do that with these numbers here. So what we have got is predicted body fat is equal to a constant value, so perhaps like a starting level. We have an adjustment for men, meaning that the equation will suit women as it is. They're like the reference level. If you're a man, you get this little adjustment because you presumably have slightly less body fat. Then we get a slight increase in body fat for age. And then we get our main term, which is the BMI, and then a little adjustment for the BMI squared. And that's a lower coefficient. That's that little kink over at the top. So sometimes this is used to develop equations for predictions, but in this case what we really just want to see is that there's a good relationship between the two, especially as we use BMI in so many studies as a measure of body fat percentage. What they were actually trying to do in this context was see if the cutoffs were appropriate for their particular population. And if we just go to the last slide, you can have a read through some of their conclusions. And they say that for a Caucasian population, it's proposed that a BMI greater than 30 is considered obese, but that threshold might not be applicable to Asians, and I imagine you've got different tables if you're working in the industry for different types of populations about what kind of cutoff is appropriate for obesity in each case.